Okay, welcome back. Today we're going to cover linking. We have talked a bit about processors and architecture, but we do need to take a step back and a little quick detour in this course about how your programs are actually assembled. Yes, we've talked about a compiler, which right now you picture something that just translates your code and puts it into binary format. We've talked a little bit about assembly, where you write something in assembly and it translates into a binary, and hopefully we've talked at least a little bit about how the compiler, actually all the compiler does is take your code, translate to assembly, and then call the assembler to produce a binary. Well, unfortunately there's another piece to this story, and that's called linking, and we'll get into why linking is needed, which is basically the fact that you don't want to have to recompile the whole program every single time you make a small change. So we've come up with a scheme called linking, where you can compile different pieces of it and then link it together at the end. And so we're going to go through static linking, object files, static libraries, loading, and then of course dynamic linking of the shared libraries. These shared libraries are called DLLs in Windows or .SOs in Linux. So we have a couple of puzzles, and we're going to talk about these in a little more detail later, but just to give you an idea, let's say you have in one file called int x, and then you have a function p1 that's defined that does nothing, and then over here you have another function called p1 that's defined but does nothing. Well, if you compile these files separately, there's no problem, but if you compile both of them at the same time, there is, because which p1 needs to exist in your final program? Well, they're both defined, so that's an error, or a link time error. And we'll get to that in a little more detail coming up. So far, just to make sure everyone's on the same page, most of us think of, we write our program, maybe called m.c, send it through a translator, aka a compiler, and then it produces a binary that can give us what we need. Now, so far that's what we've been working with. If you ever work on large projects, there's a huge problem here because one, if everyone's editing the same m.c file, that's going to get very messy very quickly. Two, it's hard to really share your code since everything's share your code with another program, because you'd have to compile the other program as well. Now you have two mains. How are you going to fix that? So we want to be able to break this out into multiple files and then compile the different files separately, and that's why we have a static linker or a linker. So a more common example here is that you may have m.c go through the compiler and assembler, translate into an object file. Now the object file is not a complete program, but it's compiled code. So a .o is binary code, but it's not a binary executable yet. It's called relocatable object files. And you'd have a.c and you do the same thing, and then the linker would take all your object files and put them together to make a final binary. This is a lot faster because this translation from a programming language, even as simple as C, to a .o is very slow compared to just linking the .o's together. And of course, this performance difference of translating is even more with more complex languages. Alright, so the compile driver coordinates all the steps. In our programs, we've been using something called GCC, the G compiler suite, and it has been doing the preprocessor, which takes all those includes, puts them together, compiles it, assembles it, and then links it. So your GCC is actually doing 4 different steps. We've talked a bit about the compiler. We've worked extensively with an assembler in this class. We haven't talked too much about a preprocessor. Just think of that as it goes and finds the includes and basically copies all the code in. So if you want to create an executable P from M, you can actually tell, well, at least in old versions of GCC, to be verbose, and it would do CPP first, then CC it with all the args, and then assemble it, and then link it down here, and then you'd be done. So GCC is actually doing all these 4 steps for you, is what's important to understand in this slide. But what does the linker do? Well, it merges all those .o's into a single executable file and then writes any extra information needed to make the file executable. So it does have to resolve, and it also resolves any external references. So for example, if you're trying to use a library, maybe printf or even some other third-party library that you might be, NoSQL, the linker's job is to put that all together inside of one binary. So it relocates the symbols and fixes up all the symbols so it all makes sense in the address space. So you have code and you have data as well. So they did want to make sure you understand that a reference might be to a piece of code. Ooh, let's not do that. Piece of code or to an actual piece of data. Why do we have linkers? Well, first off, it makes everything modular, which is highly advantageous in programming language. Hopefully you've noticed that. If not, the idea is someone can go ahead and write printf for you and then you can just use it. Someone create math libraries and then you can just use it. You know, last class I used Atlas, which was a library, and then the linker just linked it in so I can just use it as opposed to trying to come up with my own high performance matrix multiply. If you want to have a GUI, again, you can just use a GUI library as opposed to trying to write it. Also, it can save time when you're trying to compile things because you have multiple files. You only have to work on one file as opposed to everything, as opposed to recompiling the whole thing. There is actually space savings because, for example, with printf or the standard C library, almost every program uses that. And so if you have a .so that has the implementation for those functions, then you can just use one .so amongst all your programs as opposed to having every single program rewrite or inject basically the C library inside of each one. Let's see. Yeah, but memory images contain only code for functions they actually use. Sure, we'll get to a little more of that hopefully later. We do want to talk about ELF, which is the executable in link format, not something else. It's a standard binary format for these object files. That was created by System 5 from AT&T. The idea is they wanted to come up with a format about how these .o files are done, and then how we can come shared object files, .so, sometimes called a .dll in Windows. I'm not talking about Windows. I mean, obviously I'm a Linux person, but the other reason is Windows sometimes isn't always forthcoming with their information. So these are ELF binaries. It's what Linux uses. Better support for shared libraries than old a.out, sure. By old, I mean pre like 99. Okay, so when you have your program and it's compiled, it's going to look compiled in an ELF format, it's going to look something like this, where you'll have an ELF header, and the point of the ELF header is so that any program opening the file can detect what type of file it is. Program header might have any information for the operating system. We talked a little bit about page size and virtual memory segments and segment size. We are going to go more into this in operating systems, but just know that when you do compile a program for Linux, or at least in the ELF format, and Windows needs this as well, there is a header table telling it about how much memory it needs, what segments, and what the segment size are. Your text is going to be your code, so anything the .text is your code section, .data is any initialized data, and then BSS is a block, started by symbol. It's pretty much uninitialized static data, so if you have any global data that's not going to change, it can be put in here. The rest of these I've learned are optionals, but most of these are if you compile with -G, they will add some symbol tables and some debug information, and this is so that if there's an error in your code, you can attach the debugger and it can figure out what piece of code is executing inside the compiled binary. Because remember, your C code is not what's being run, it's the compiled binary version that's been generated from your C code. So this information down here will map the text segment and the data segment, the BSS, to actual C code, so if you have an error, it can detect where the error is and then tell you. This is incredibly helpful when it comes to debuggers. Now, let me go ahead and show you real quick that this stuff does exist. I've gone over here inside of our csci 330 Spring class code and linking. I've created a simple.c program. It just says hello. I didn't even bother to write the word world just because I want to make it simple. If you do gcc simple.c, alright, that goes to compile. You get an a.out file. Of course, we can run it, and it says hello. If we want to see the contents of it, we'll have to do an ojdump-big D on a.out, and it's going to spew a whole bunch of information, which is going to be hard to review on a small terminal. So let's go ahead and dump it to a txt file. and I'll open it up. Alright, we have a bunch of different A.out file format. It's an ELF64 x86-64. Basically, it's saying that this is ELF 64-bit, and it's meant to be compiled and run on a 64-bit x86 machine. You'll notice that some of this should look somewhat familiar. This is a different form of x86 assembly. It's the GCC version, not the NASM version, but it should look at least somewhat similar. Don't worry too much about the syntax, because I'm not going to be grading you on that right now, but there's a couple things we want to look into. Notice we have different sections. Now you'll notice that there's more sections than what I listed out earlier. I don't have time to go through all these, but let's go and look at the .text section. Simply of .text, hey look, it's _start. And the reason for the _start is that is where your program, wait for it, starts or begins. And if you read this code, what it's actually doing is setting up, first it sets up EBT, basically your stack pointer, sets up a couple other things. Here's your stack pointer. Saves off some variables for what, when someone calls, when the operating system calls it. And then it's going to link up a main, and then it does a call on main, and then, what was that, high less than, and then it returns. So it's going to call main. Here's the call to main. And let's see if we can find main. Yeah, here's main. Push, move, 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 and then looks like it's calling something in STI. STN used. Interesting. And it's going to call some function, probably from AK printf, and then it's going to return down here. So here is our code inside of that section. I just wanted to show you that these sections can be reviewed if you choose to, using something called objdump, which will investigate the binary file you have. Now, it's really just important that you know that these ELF binaries contain these sections, namely the text for your code, data for any global data, BSS for any static data, and then this stuff is optional if you included debugging, -G, and that'll help with debugging. All right. Hey, look, simple table. This is all the information for debug. So here's some example C programs. Notice that m.c has main and a.c does not, but m.c is e equals 7, main, r is equal to a call to a, and then it exits. All right, over here we have e, which we're going to extern. Okay, this is a way to tell C that this e is going to exist in a different file, namely right over there. We're going to create EP to be a pointer to E. All right, x equals 15, y equals 7, and then you're going to return the dereference of EP plus x plus y. Okay. So the question is, how do we get this to link back to here? Well, when you compile this, it just has information saying, hey, this E is going to point somewhere else. Make sure you have an EP that is going to point to it, and then do these calculations. All right. Well, how does this actually work? Well, you have in your different O.O files, you have your code and then some data, and then down here BSS for some static. And so it's going to keep track of what all this data is, or code, and then it's going to actually assemble it or link it all together. Is this slide just cut off? It's just cut off. Well, that's interesting. All right, link it all together into a final ELF format. So symbols are lexical entities. We haven't talked about compilers, but just know that a symbol is some type of variable or function name. And each symbol has to have a value, typically a memory address. And code consists of definitions and references. And then the references, definitions are the actual definition of something. So for example, this function is defined as being a return, etc., etc. And then a reference, aka here, E is referencing this one over here. References can either be local, as in they can be inside of this file, or they can be external and be in another file. So local symbol E, return to external symbol exit, because that's in some other library code. Reference to external symbol A, and then we have, let's see, ref to external symbol E as well, because remember E is defined as external to be over here. P is a local symbol, and X and Y are other local symbols as well. Definition local symbol A as well, and then it's defined right here. We can go and look through all the section here. Now this is an example of what was compiled using GCC, a 32-bit version of GCC. Notice that main might call main plus some, jumping to some value down here, and then this is where we're going to exit as well. So call to A and a call to exit. All right. When you're looking at the a.o file, let's see what we have here. We have EP, we set up here. All right, just know that all this code does map to assembly on this side. And then it's all linked up. And I think the point they're trying to make here, let me bounce back, sorry for it, is that notice that the stuff highlighted in red, call to something along this line, is going to change. So notice in main we have a call to some address because we don't know what it is. But when we go to the final piece of code, now we have a different address because the linker said, oh wait, this needs to change in order to what value A is going to be. Well, I'm going to link A to be over here, and then I'm going to update the value right here. This may be confusing because you might think, well, why isn't this value down here? Well, it's really just an offset jump. So notice that 3 to 4 here. So this was an offset. So the idea is that the highlight stuff in red is what the linker is going to fill in when all the object code is put together. Notice that none of the code itself was rewritten. The linker is simply editing or updating or touching up all the different memory addresses so everything links and aligns correctly. That's all the linker is going to do. Let's see. Executable after relocation to .data. Oh, okay, so the EP will notice that, hey, look, okay, this EP is actually pointing to this guy up here, which is the E section. That's all they're trying to say. So it does link up the values of certain data. Like I said, it's only updating the memory addresses. Okay, off to some little linker problems, which you will see on your final exam. So program symbols are either going to be considered strong or weak. Strong is procedure or uninitialized globals, or initialized globals, and weak is uninitialized. So, for example, int foo equals 5 is strong because it's been initialized global, and p sub 1 is strong because it's an initialized procedure. Int foo is weak because we did not initialize it to a value, so it's a weak symbol. And p2 is strong because we're actually initializing it here. So some rules. A strong symbol can appear only once. This should make some sense because you have two files. If both files had p1 defined in them, that would be an error because which p1 are you referring to? On the other hand, if int foo is defined here and then you're just saying that foo is going to be used over here, then that's okay because you only have one foo. A weak symbol can therefore be overridden by a strong symbol of the same name. So once it finds a strong symbol, the linker will override all the other weak ones, but if it finds another strong one, it'll throw an error. If there are multiple weak symbols but no strong symbol, the linker will choose an arbitrary one, which may or may not be what you want. The rules aren't made to be broken, but they can cause issues. Here we go. Wow, it didn't even give me the slow readout. So we'll just go ahead and go by them. So you have int x and p1 up here and p1 over here. Link time error because you have two strong symbols, p1. So that's example of a linker error. Notice that this, if you compile it in GCC, this would to an O file. Sorry, this compiles to an O file just fine. This compiles to an O file just fine. But it's when you try and link the two that you're going to get an error. References to x will be the same uninitialized int, but is that really what you want? You know, which int it is chosen. Hopefully that was correct. But in general, you should initialize at least one of your symbols, which would make it strong. All right, here's an interesting one. You have x and y and then p sub 1, and then you have x over here with a different type. Well, writes to x might overwrite y. Why is this? Well, a double is 8 and int is 4. So if you write to x, you might also be writing to y as well. But that's perfectly legal in the linker. Modern linkers will give you at least a warning about this, but keep in mind that technically this is okay, or this is correct code. It's just going to produce something that you do not want. Writes to X and P2 may overwrite Y again, even though these are strong. This is now a weak symbol, and since you're referencing it as a double, it's going to take X and then treat the X and Y possibly as a double, and then you might be, again, overriding Y. Again, you have to be careful. Modern linkers will at least give you a warning here. And then references to X will refer to the same initialized value over here, which is probably what you want. So P2, if it says X equals something, or I want X, it's going to jump over here. All right, another nightmare scenario that we are not going to be able to talk about too much in depth because we haven't gone into how structs and alignment work. If you have two identical weak structs compiled by different compilers with different alignment rules, well, who knows how you're going to reference each piece of data. And that you can think of this as a class that has different data inside of it, and one compiler arranges the data one way and the other compiler arranges it another, and then someone has to try and link it all together. Yikes. Alright, packing commonly used functions. Okay, so we've talked a bit about linking. We've talked a bit of some of the problems there. But one thing we haven't talked about is you have all these .os. There's probably code that you want to use amongst all programs, like for example math functions or your printf or maybe some NoSQL or whatever. How can we basically make it so these can be usable by all programmers across the board? You might have math, I/O, memory management, or string manipulation. So option one, put all functions in a single source file, and then everyone is given that source file. It's guess space and time efficient because the compiler can really compile it all down. Another option is push each function into a separate source. Programmers explicitly link what they want to. More efficient, but can be very burdensome. So what, one solution here is to have a static library. This is a .a. This is not a DLL or .so. This is a .a. We'll get to the DLLs and SOs later. What an A is just a concatenation of all .o files into a single index. And so they enhance the linker so they can try and resolve unresolved references by looking at all the symbols inside of a .a. If it finds a reference, then it takes that .o file inside of a .a file and puts it together. Let me show you what I'm talking about. Let me go over here, jump out. Let me go to locate libpthread.a. Oh, we got all sorts of ones in here. Hey, here, let's use this one. So this is a .a file. This is a static, not an SO. This is a static. And you have a program called AR. Now at AR, and I did a little help, there is an option right here, T, to display the contents of an archive. So I'll do AR space T, and then I'll go ahead and take this, and I'll paste it. And hey, look, there are a bunch of .o files right here. So these are all the .o files inside of our libpthread.a that were compiled and then put inside of an A file. If you actually, really all a .a file is a zip of .o files. That's it. And so you have your .o files inside of your .a, and the linker has been enhanced to be able to look through a .a file, and if there's an O file that you need, maybe this guy, it will take it out and compile it into your program. One last trick, if you want to know how many files are in a .a file, since that's going to definitely be one of your homeworks, you can pass it to WC, which is word count, and that first thing it gives you 221. Boom, there you go. That's how many files are inside of libpthread.a. Okay. So let's see. So when you're trying to link, you might have p1.c, p2.c. That goes through your translator, aka your compiler and assembler, to put a .o file. And then linker is going to take your .os, and then maybe a libc.a file to produce a final binary. Alright, and this does improve modularity substantially because now we can just give everyone a .a file in order to produce a final binary. Alright, that's great. You can create static libraries by compiling all your .o, send them through an archiver, ARRS, all you're calling it libc.a, and then give it all the .o files, and now you have a .a. and this is still commonly used. Now, yeah, so commonly used files, you have liba.c. I guess this guy was only 8 megabytes of 900 object files, a little more of that nowadays. libm, 1 meg of 226, and you can go ar.t to go find it and then sort it out, or as I did, .wc to see how many there are. But you'll notice that when you list them all out, they usually have one .o file for every single function you want to use: fork, printf, scanf, etc., etc. And here's all the ones for math as well. So the linker is able to go ahead and basically link them all together. One thing they do want to tell you is that linker's algorithm for resolving references, it scans the .o's and then the .a in the order that you put them. So always put your .o's first and then your .a's at the end. That way, if there's any type of conflict, it'll take your code as opposed to the static library code. All right, we're going to skip this for now because we're going to go into something called shared libraries. All right, we talked about static libraries, which copies the code directly into your program. That was not the final step in the evolution of the linker. Linkers are still evolving, so to speak, but the next big step is to have a shared library. You have all these .a's, and with the static library, it copies the code and puts it into your binary. Well, everyone's going to be using the libc, or almost everyone. Most people are using libm and all these different libraries. So you're having multiple copies of the libraries running inside of different processes. And if you have hundreds of processes, that's a lot of code that's just being copied over and over again. So what a SO is going to do instead is the program, the final executable is going to say, hey look, I'm actually dynamically linked against libc.so, and then when the program is run, that is when the operating system is going to take the binary and then hook it up to a libc.so that already exists in memory. That way, only one libc has to exist in memory, and multiple programs can reference the same libc. This will substantially reduce the amount of memory that your programs use, and also disk space as well. And that is the point of these shared libraries. Let's see if we get a nice little picture. Excellent. So we have your translators, puts into .o, the linker then says that, okay, we're going to link against libc.so to produce the binary. Notice that you have your binary here. When you run your binary, it's going to call ld.linux.so, which is going to go back into the binary and then link up to the shared objects that exist in memory, and then run the program then. So the idea is that your binary is here, but the final executable still has one more linking to go through before it's run inside of memory. It's important to realize that your program, your linked program's on the disk, and your program that needs to be linked is on the disk, and the final linked program is going to be inside of memory. Now, how can you see what's being linked against? Well, let's go in here. We have a.out. We'll do ldd a.out. And here we have Linux VDSO. That's the, I don't remember what that one is, but here's libc. And then here's the actual linker for my program. So you notice that it's linked against the linker. It needs to load this libc.so. It actually tells you where it found it. And it also is going to use this one as well. And if you have other things you're linking against, it will go and list them all out. And the command for this was ldd, and that's the one that gives you a list of all the things that's linking against. You'll need to use this for your homework. Alright, so another complete picture. You compile your different O's through your compiler and assembler to produce the object file. You might have a stack library that you want to link it together to produce a binary. And that binary says I still need to have libc.so and libm.so. So when the operating system tries to load it, it goes and it finds the .sos, links them in dynamically, which means that the program in memory is linked up to the .sos. So you might have seen some of this with DLLs not being available, or .sos. That's why you need to install some extra binary code, which are shared objects. What's a shared object? I didn't exactly go through it, but it's basically your .a, but with extra wrapping around it so that the operating system can load it. All right, and I think that's going to be all for today. Great. That is all for today. Let me go up to ScrumDo real quick. Hopefully I can get into here. So your question, answer the following questions, familiarize yourself with the tools manipulating, write down the commands you use to get your answer. The easiest way to do this is write the command, hit enter, copy and paste your command and the output, and then copy it and then paste it right into here. How many object files are contained in the version of libc.a and libm.a on your system? Hopefully you have a Unix system right now. If not, contact me to where you can SSH into one, but I'm pretty sure everyone here has had to have one for the assembler. Does GCC-02 produce different executable code than GCC-02-G? So, what am I talking about? Well, over here you have GCC. I can do -02 on, what do I have? Simple.c, and that'll produce a binary. And then there's 1-G, and that'll produce another binary. So the question is, are the two different? Go ahead and take a look, and if they are, make sure you figure out why. Hint, objdump will probably be helpful here. What shared libraries does the GCC driver? This is usually user bin GCC. If you don't know where this GCC driver is, you can just do a which on GCC, and then I'll tell you where it is. Go ahead and just write what you have here, and then or show me with the screenshots. Let me go ahead and save that, and that's linking, so we're going to put that in all your base right there, and that's going to be all for today. Next class, we're going to talk a little bit about multiprocessing, and it is going to get a little complicated, but it is one last very important topic, and then we'll hopefully either do the review that day or on Monday. Monday is when the projects are done. We're going to need to do a virtual meeting of some sort with the class on that day, so I can go ahead and ask a couple of questions. So be ready to at least have a virtual meeting on that Tuesday, hopefully at 9:30 during class time. And then we can also do a review then for your final. All right. So with ScrumDo, we're definitely getting towards the end of ScrumDo's license, and ScrumDo is starting to give us a lot of problems. I am trying my best to convert everyone over to Kanban. It is the end of the semester, so there are a couple of issues, but I will be working to get everyone converted over as soon as possible. Hopefully I can get that done by the end of this week, and then we can just be working there. I do plan to finish grading, and at least grading Gate 1 and Gate 2. That way we can have a final score for those two gates, and if there are any issues, you can go and talk to me about it. All right, that is all for today. I will see you on Thursday.